Hello everyone, welcome back. So let's try a group problem. So once again, grab a friend, grab your dog, grab a rubber duck, whatever is necessary, and let's do this problem. Now what do we have here? Well, we have a force P. We're applying it to move the wedge A to the right. Moving it to the right. Impending motion. The spring is currently compressed a distance of 175 millimeters. That's the start. We know what the static friction coefficient is for all contacting surfaces. But you notice there's a rollers right here, so no friction. We can elect the weight of A and B. It's a little easier on us. So we want to know the smallest force P needed to move wedge A. Remember, we're trying to move it to the right. Okay, so what's your plan? Okay, I'll allow it. Your plan is to draw free body diagrams of the blocks at B and A. You're going to apply the equations of equilibrium to one of them. It says to block B. And then finally to wedge A to solve for that force. Now, question for you. Why A? Why a second? Because honestly, if you're trying to solve for P, most likely you can't do that in one go. So you don't have any point in solving the equations at A until you've done it at B. Because you're probably going to need this info to solve it at A. That's just how it's going to work. Okay, so in 3, 2, 1, you're back. You're back. You've done the problems. You're like, oh my goodness, they make so much more sense now. My dog, he's incredibly helpful. And the rubber duck really gave some insightful commentary. If you hear your ducks talking to you, send me an email. Let's talk. So let's look at this together. Okay, first off, we're looking at the in block B, which is really nice in many ways. Because in block B, we see there's a forced spring right here. We also have a normal force at the bottom. We have a frictional force. Like, wait a second, where's this coming from? That's from the wall. There's no friction from that wall, but it is pressing against it. Wondering why there's no contact force over here? There's nothing pushing into that wall, so there's no contact force. Now we can calculate the spring force using our spring formula. We know what the stiffness constant is, and we know how much it's compressed. So it comes out to be 2.625 kilonewtons. That instantly lets us solve for NB, which will let us solve for FB, which will let us solve for NC if we really wanted to calculate it. Do we even need to calculate NC? We can. So if this wedge is on the verge of moving to the right, then we know that slipping will have to occur on both contact surfaces. So this is why we can use this equation. If it's slipping, we can use this. If it's not slipping, we can't use that. It's because motion is impending. That's a very important little detail. Okay, now we're able to solve all these equations fairly simply. But we don't really even need to solve the sum of the force in the x equation because this is not actually necessary for anything else. We just need to do the frictional force, which only requires that we know our normal force. So we just solve that, we get the frictional force. And now with this, we have more or less two unknowns. We have two equations, plus some moments we had some sort of size here, but these are all just applied more or less on the origin or on the center of gravity. So we look at it, some of the forces in the y, some of the forces in the x, and it's beautiful. It looks good. Now, where are these angles coming from? We have cosine of 10, sine of 10. We have cosine 10, sine of 10 right here. This is all coming from these points. We're breaking up the frictional force and normal force into its x and y components. So as usual, if you're struggling with this, draw it big. So I'm going to do it for the normal force, and I'll let you do it for the frictional force. And so to connect that, I have to draw my arrows like this. This would be the normal force y. This would be the normal force x. This is just the normal force. And we have an angle of 10 degrees. Now, depending which angle I use, that determines the trigonometric functions I use. So adjacent over hypotenuse is cosine. So to get the y component of the force, I would use in cosine of 10. So that's right there. And to get the x component, it's opposite over hypotenuse. Opposite over hypotenuse is sine. So to get the x component, it would be sine of 10 times n. And we see that right there. Sorry, we plugged in 2.841, so I got a little bit confused for a second. And similar things would happen with our friction. Once again, if we look at this, you can see that we can avoid all algebra for character. Like right here, you've technically done algebra in the fact that you have this very simple equation, so you went ahead and plugged it in for the frictional force A. But like there is no required algebra here. It's one unknown, one equation I can solve. And then for the second equation, we have P. So be very careful about the order of these problems. They're honestly not that hard, except you have to remember what direction motion is impending. If you don't know that, then things get a little bit more difficult because you have to make an assumption and then check your assumption, which can be really annoying when you make the wrong assumption. You do all the equations and you find out I did it wrong. But in the end, there's only two directions it can go, so it's not too terrible. Okay, well, we'll stop here for now. Remember, if you're struggling with this, please reach out to me. I would love to hear from you. I would love to help you. And also, as a note, if you have any questions you'd like to work out, examples you'd like worked out, and you can't make it to a problem session, send me an email. I'll work them out in the problem session, record it, and then post that recording for you. Well, I hope you've had a wonderful day, and I'll see you all next time. Bye-bye.